Okay, hi, hello everyone. Welcome to section number 4. We are really in it. Exam scores, I think, were just released. How are people feeling? I did not see a lot of the exam. I graded the fused chair question, and then I graded one of the sections of the last question. And on my questions, people did pretty well, but I have not kind of seen the whole lay of the land. But I think that the protocol is going to be the exact same as the PSETs for regrades, which is if you believe something should have a regrade, reach out to your TF, so me first, to ask about it, and then you can submit an official request. But you've made it through the first hurdle, your first organic chemistry exam, which is a lot. Yes, does anyone have any thoughts that they would like to share? I can pause the recording if you would like to share thoughts more candidly. But I feel like y'all did pretty well. Maybe while people are thinking or typing, I'll go over the game plan for today. So if you want to scan the QR code for today, I think that the question of the day is, what was the song of the summer? Which I hope that wasn't the one I used last week. Lectures 3 and 4 for the fall are switched from how I do it in the summer. And so I'm I might have gotten the spreadsheets mixed up. Then section 4, or lecture 4, was really the first lecture where you learned organic chemistry reactions. And to be so honest, that's going to be the rest of the course. And so we are going to spend some time, first off today, kind of going not just normal section kind of working problems, but talking about just the skill of how do we study reactions, if that's going to be kind of the game for the next part of the class. Then we'll go into the actual kind of reactions, so we'll talk a little bit about redox reactions, particularly oxidation. Then we'll talk about hydride equivalent reactions, carbanion equivalent reactions, and reversible carbonyl additions. So I think I'm going to just jump into it. So first off, how to study reactions. This is going to be a 3-part little series where part 1 is happening now, and then I'll sprinkle in how to study reactions part 2 and 3 later on. But to start off with how to study for reactions, you first need to know how you're going to be tested on reactions. So there are 3 kind of big ways reactions are tested on exams. So the first type is based on what we call the line reaction. So the line reaction is essentially we can write an entire reaction on a line, basically, where we have some sort of starting molecule, then we have an arrow where we put other reagents, solvents, or reaction conditions, and then on the other side is a product molecule. And line reactions kind of give you an overview of what it is when we talk about a reaction, what is the reaction accomplishing. And then the other part of a reaction is the mechanism, so the curved arrows, the homo-lumo interactions, and all of that. So line reactions form an amazing template for exam questions. So essentially what we do is we take one of these 3 parts and we put a box over it. And then we say, you fill in said box. So it might be that we give you starting material and the reagents and say, okay, what's the product? Or starting material and product, and we say, what are the reagents we should use? And then the kind of harder one is if we give you a product and some reagents and asking what was the starting molecule. Don't worry about these specific reactions here. You have not learned all of these. This is just kind of to give you an idea of what it looks like and the type of question that you'll be asked. So first big type, box problems. This will probably be at least a full page, if not 2 pages of your next exam. It happens a lot. Second type of question is the mechanism question. So we would give you a full line reaction, and we would say, provide the full curved arrow mechanism. And as a part of this, we might ask you to identify homo-lumo interactions or different orbital things going on. We might ask you why one product is formed instead of another, and you'll have to kind of rationalize it using what you were taught about the kind of quintessential core reaction. And with mechanism questions, they really come in two flavors. One flavor is feels a lot more comfy. It's a known mechanism question. That's one where, like, essentially what we want you to do is regurgitate the arrows from lecture. Like, beat for beat, you should be able to copy the arrows going to these atoms or bonds and reproduce the mechanism almost exactly. And, like, if you had your notes, you would get, like, full points on this. It's an easier type of question. The slightly different flavor of mechanism question is a little bit harder, is a, quote, new mechanism. But do not freak out, because the new mechanism can't be that new. Like, we can't throw you in deep waters of things you've never seen react before and just expect you to figure it out. Like, we are really only going to test you on things that are really, really similar to what you have seen before in lecture directly, maybe with one step that's a little weird, or like one small change. Like, imagine, again, this is just kind of an example, you learned all these reactions of carbonyls. Well, then what if on the exam we put a sulfonyl? And it's kind of like, oh, okay, like this should probably react similarly to a carbonyl because oxygen and sulfur on the same column. Or like there might just be like one step that is different. But you're going to see more practice of this as you get through the problem sets. So you definitely are going to get a feel for what these look like as the course continues. So don't be super stressed. The last big type of way that reactions are tested broadly are questions called synthesis questions, which you are not going to have a capital S synthesis, big boy synthesis question for this course. But I do want to talk about it because it shapes how we want you to be thinking about reactions. So a synthesis question, the essential setup is we'd give you a starting molecule and a product molecule and say, using like 7 to 10 reactions, get there. And it's a really classic type of question for most organic chemistry sequences. And at most other universities, they are doing syntheses, like long syntheses like this. We are not covering in this course because Harvard does this weird thing where we abbreviate essentially all of organic chemistry, a year's worth of organic chemistry, into 17. And then Chem 27 is biochemistry. And it counts for organic chemistry credit and everything. And we do like the curved arrows of biochemistry. But it's just because of how we set up the course different that is why we don't test you on synthesis. That being said, because this is such a big thing in chemistry, and like thinking about all of our reactions as kind of tools to accomplish different goals, you are going to have kind of baby syntheses. Like we might do something where we give you kind of a flow chart thing and you have to like fill in parts of it. So you aren't going to be fully thrown to the wolves of just start and then do all the things to get there. But this type of thinking of how do we build molecules really is like at the core of a lot of how we want you all to be thinking about reactions. So we have these kind of 3 ways of testing reactions. And again, y'all are really going to mostly just have these first 2. But just some general advice before we get into a specific study approach, because I want to spend some time like giving you a tool to try to do with some of these reactions. A lot of times, the instinct for many students in organic chemistry is to study the material over and over and then try to do practice problems once you are finished studying. That doesn't really work well for us, mostly just because the pace of the course is working so fast. And then also, a lot of times I'll get students into situations where they really understand the chemistry, but then when they're confronted with like a blank exam page for reactions, they can't deliver and just kind of work through a reaction. And so a lot of this is use the practice problems as an opportunity for your studying. It shows you what you do and do not know yet, and it really is going to be the kind of most high yield way of studying. I'm also like very guilty of like not doing this and doing studying that feels good, which is like recopying down notes. But it's the thing of like, if you have all the time, go for it. You know, like, you know what works for you. But just when time is an issue, as it probably will be as we start to have 60 reactions or 70 reactions as we get into the course, then I would highly encourage you to do kind of more of the active recall learning as you work problems. So the challenge going forward, because the first few lectures is a little hodgepodge city of like, okay, naming, okay, Newman projection, stereochemistry, all these things. The rest of the course going forward, we are going to give you 7 to 12 reactions each lecture, and that will be it till the end of the course. That's kind of like how it is structured. And so the students who typically do the best in the middle and late part of the course are students who learn very quickly how to take in a new batch of reactions and internalize them and get to where they can work with them and answer these types of questions. So know that that is the challenge going forward, and that is the game that you are playing. The other thing is just thinking about these reactions. I think that one other big challenge with reactions is sometimes they'll just feel like a deluge of like, here's a bunch of information. And we need to think about kind of how do we organize all of these reactions and put them together, and like why is it being taught to us, and how can we like make a framework for this. And so the metaphor I really like to use is reactions are tools that accomplish chemical goals. And you could have a toolbox of tools that looks like this. And if you are doing some home crafts, that is fine and dandy. That is great. When you are having to take a timed organic chemistry test, you want your toolbox to look like this. And so one way that we are going to think about organizing reactions is grouping them into families that have similar mechanisms or accomplish similar goals. And I'll kind of show that as we get into the study method. But any questions so far on kind of like, what are reactions? How are y'all going to be tested on reactions before we get into, let's try this study strategy out? Do you think this method was correlated to the exam 1 grade? So this, what I'm talking about, in no way correlated to exam 1 grade, because exam 1 grade is hodgepodge city. You know, like the rest of the course is going to look very different in terms of what we are asking you to do, because the rest of it is all going to be about reactions and how you put them together. So this is the thing. If you did poorly on exam 1, do not worry, because you will have much chance for redemption with the rest of the course. Like, again, they are very different kind of skills. They do kind of build on each other, but we're not going to have a question on exam 2 that's just draw a chair. Like, we're not going to have a question that's just do a Newman projection. They become kind of part of the fold in your tool of arsenals, or arsenal of tools, I should say. And then the other flip side of that is if you did well on exam 1, don't relax. You are entering the woods. There are wolves afoot. But we can do it. Cool. So let me show you. This is kind of my method that I use for studying reactions. And it's one that I kind of have developed over the past like 5 or 6 years. I will say I did not like come up with this idea. I've just been trying to like concretize it, make it concrete, and try to like blow it up. The big idea is when you are studying reactions, you need to study them at different levels of detail. So, for example, and we are going to kind of trace this along with one of the reactions from class of the hemiacetal formation mechanism. And specifically, we're going to look at the hemiacetal formation in acid, and there was also a version in base. But let's kind of see what these different levels of details are, and then we'll talk about why we should kind of focus on different levels. So starting off, it's the full mechanism. It is like the whole shaboom, like the full curved arrows, all the structures being able to generate from start to finish, and the homos and lumos. So what I've done is I've written out the full curved arrow mechanism. And can we just take a minute and talk through what are some like the homo-luno interactions going on here, and like why are they happening? So can someone help me out with this first step? What's our donor and acceptor?
Is our donor the like
Yeah.
And is our acceptor sigma star HO or OH?
Yeah, you are exactly right. Sigma star OH. We break the sigma OH bond, so we put electrons in the sigma star. Excellent. So, okay, when we did this, we protonated a carbonyl. And then, why did we do this? Like, maybe let's look at the next step. The next step is our alcohol attacks. Here, we have a lone pair on oxygen attacking the pi star CO. Why did we do this? Why did we not just have this go and attack the carbonyl directly? Any ideas?
Is it because the lone pair on O is more electronegative and that other O is positive?
It is related to that. So, like, the lone pair on oxygen, it's going to be attacking either way, though, right? So, whether it attacks this or it attacks this one. The difference is going to be in our electrophile here, right? So, if this is our electrophile that's being attacked, how does protonating it make it a better electrophile? Because that must be what we're doing, right? Like, there's not another reason why we would protonate the electrophile if it didn't make it better to react. So let's
Because
think,
of
go
a
ahead.
positive charge, right?
Yeah, so I mean, one of it's just electrostatics, right? So like, if you have a lone pair that has some partial negative, you want this to have more positive, right? And if you have a positive on this oxygen, that's making this an even stronger dipole, so then you have a bigger partial positive on the carbon. Totally. But can we think about it in terms of the language of molecular orbital theory? So the big thing that we had in molecular orbital theory is we had a HOMO of one molecule and a LUMO of the other molecule. And then we said that there's often going to be a gap in energy between the HOMO of one molecule and the LUMO of the other molecule. And reactions that are more favorable have the HOMO and LUMO closer in energy. So imagine like you have the LUMO up here, the HOMO up here. A reaction with a big HOMO-LUMO gap, it's not going to happen as readily. It's not going to be as stabilizing. Versus, if you have a smaller HOMO-LUMO gap, that's where they were like almost the same energy, and so they were much more stabilizing and would happen more readily. So what we did when we protonated this carbonyl is, what are we trying to do with the LUMO on our electrophile? Do we want to raise the energy of the LUMO, or do we want to lower the energy of the LUMO? We want to lower it, exactly, to decrease that HOMO-LUMO gap. So our kind of Y here is to lower the energy of the pi star CO LUMO. Excellent. And again, I know that this feels really in the weeds here, but like, to really understand the reaction and why we are doing it and why these steps happened, this is the kind of level of detail that's super granular. Okay, well then in our last step here, we had a lone pair on oxygen, and we broke this sigma OH, so we put electrons into the sigma star OH. And then we get to our product. So, like, that is fine and dandy, but do you see how we've kind of gone through that, and it's, like, still unclear, like, what's the forest, what's the trees? Like, what is this whole reaction? What are we doing and why? And also, the other big challenge is with curved ER mechanisms, the entire language of what we've just done is visual. And y'all have a lot of skills for studying facts. Y'all have a lot of skills for studying like algorithms for like solving math problems. But like studying visual information is something that's just a little bit tricky and different. And so let's try to zoom out a little bit, one layer. And now what I want us to do is, for each of these sub-steps of the reaction, let's try to summarize the mechanistic logic. And what I mean by that is just, can we literally, like in plain English, or like plain English for a chemistry class, just like in a few words, describe what's happening in the step? So like, how would you describe this first step in like 3 or 4 words?
Oxygen gets proteinated.
Yeah, that's great. I am going to phrase it very slightly differently, but it's the same exact idea. I'm going to say protonate the, and I guess I'm going to cheat a little bit. I'm going to do carbonyl as like this. Okay, we protonated the carbonyl. Anyone want to take a stab at step 2? What's happening? I'm thinking like 5 or 6 words for this because it's a little bit harder to describe.
A nucleophile attack.
Yeah. And maybe let's just be a little bit more specific. So how would you describe our nucleophile? Maybe with like a functional group name, right? Because functional groups are a way of tagging molecules to see kind of motifs of how it's going to react. So let's call this like an alcohol nucleophile attacks. Well, what's our electrophile? Well, it's a carbonyl electrophile. Okay. And then what's step 3? Well, we're removing a hydrogen. So I would just call this a deprotonation. And maybe to go back to the Y here, it's just to neutralize the molecule. Neutralize the product. Okay, so we're able to kind of zoom out just a little bit. We have these 3 steps. Then what I can do is I can start doing things like listing out my steps, my mechanistic logic here. And this creates a much more manageable flashcard that is in English that you can use. And it also just kind of describes the beginning, middle, and end here, not with arrows. And the idea with these labels is you kind of want it to have enough information that if I give you a starting molecule and I give you these reaction summary things, you would be able to like draw the full curved arrow mechanism. You want a shorthand for you so you're not just having to learn this by just drawing out the mechanism over and over again. But moreover, we can start to think about what is the logic behind these steps. So you really have only seen 3 types of arrow pushing in reactions so far. The first is acid-base steps, which we've been doing since I think lecture 2, right? So protonation, deprotonation, and then if we do a protonation followed by a deprotonation, we call it a proton transfer. You'll see that more in lecture 5 on Thursday, the specific language of that. But those are arrows that should by now be feeling pretty comfortable. Like if I told you to protonate a carbonyl, that's the thing of, you can imagine a carbonyl, you know it's going to be the lone pair in the oxygen that's going and grabbing a hydrogen from some acid. And so like here, this would be just from H3O+. But like you're going to be getting to the point where you can start to imagine that in your head and you don't have to draw it out every time because you know how to do a protonation. We also have deprotonation being the same logic of just removing a hydrogen. And then the other big type of logic that we see in lecture 4, and we also see it in lecture 5, is an alcohol nucleophile attacking a carbonyl electrophile. So that is like the core of all of the reactions that a nucleophile attacking a carbonyl electrophile is the core of all the reactions in lecture 4. Then the last type is going to be a lone pair push, which we don't really see in this Ford reaction. But if we did the backwards reaction and we were trying to go from this all the way back to here, we would have to do a step over here where we push off a molecule that attacked. So like essentially we need to undo this step where the alcohol nucleophile attacked the carbonyl electrophile. And to undo that, what we would do is not all this. We would push down from this OH and kick off the HOET. And that would take us back here. And so that kind of push and kick someone out, that's called a lone pair push. And that's just the 3rd type of logic that we see. Okay, so we've zoomed out a little bit for the mechanistic logic. But now let's zoom out even further beyond the mechanism and think about the line reaction. So the thing I will encourage you to do is study line reactions as distinct pieces of information that are connected to the mechanism, but you should not have to think through a full mechanism to do a line reaction. Because remember, if you have a page or two of the exam are all box problems where you're doing these line reaction levels, you don't want to have to mentally write through all the curved arrows just to get the answer that they want if they just want a structure. So, a couple of things. One thing that we should do is we should think about, okay, if this is our line reaction, how can I give myself instructions for how to just draw the product given two starting materials? So like imagine I had covered this up and I want to give myself instructions for how to draw the product. Well, this is going to sound kind of crazy, but I love a fake mechanism. And a fake mechanism, instead of using arrows, says things like erase this, connect this. Like it's like, imagine you are giving instructions to your friend who is not in organic chemistry and you're having to have them write all your answers for you. So like for me, thinking about how to go from this structure to this structure, or like these two structures together, the thing I'm thinking is 1, erase the carbonyl. 2, add an OH, and I'm going to call this OR in its place. And that comes from this idea that here, our alcohol, this is really some carbon chain and an OH, right? So to figure out what is plugged into the molecule, in this case OET, well, it's this OR part. If we instead had used methanol, MEOH, then we would expect this to be OME in the product. Or if we'd used like propyl, we would expect this to be with a propyl. I should add one more carbon if I'm going to call it propyl. So that's kind of like what a fake mechanism looks like to me in terms of just being able to draw what the product is. So can you take a second and try to draw what's the product of this reaction going to be? To go from, and our reaction starts with a ketone or an aldehyde, and then we form a hemiacetal or a hemiketal, which I'll talk about in a minute. So take a minute and try this fake mechanism out on this example to see if you can just draw what the product looks like. So, my step 1, I just erase the carbonyl. Okay, so we have our little hexagon. And then in the place where I erase the carbonyl, I need to have an OH, and I need to have an OR. In this case, my R is going to be all of this. It's going to be 3 carbons. So I'm going to write my O, and then I'll do 1, 2, 3. Bada bing, bada bang, we've drawn the product, and we didn't have to do the full curved arrow mechanism. Woot, woot. So this is a type of skill that for every reaction you learn, you want to be able to just draw the product. And likewise, because these are reversible reactions, you want to be able to do the opposite. And it's actually much easier in reverse. Like if we had to do a fake mechanism to go from over here to the starting material, it literally is find the carbon connected to 2 O's, erase all the O nonsense, and put a carbonyl on it. So I think it's a little bit easier to go in reverse. So this, again, will let us move quickly at this line reaction level. Now, one thing here is the other thing that's going to really help us if we zoom out even more past the line reaction level to just does this reaction exist? Why are we teaching it to you? What is its purpose? And how can we like generalize this and think about kind of where we place this in the toolbox? Oftentimes, I make a difference here between the goals of a reaction and the purpose. I think about goals as like SMART goals, like the actionable, like achievable, blah, blah, blah. To me, goals are what bonds are made and broken in a reaction. And then we can start to see how the different steps of the reaction accomplish those goals. Purpose is like what's your life's purpose? But the purpose for most chemical reactions is generally to convert from one functional group to another. And like that might sound a little basic, like you might have a much grander purpose for your life, but for these simple reactions, they just need to accomplish one thing. And so knowing their purpose helps us kind of generalize this. So the purpose of this reaction would be to interconvert, because it's reversibly, between a ketone or aldehyde and a hemiketal or hemiacetal. The only difference between a hemiketal and an acetal is whether or not there's a hydrogen. So like, for example, for an aldehyde here, we said there's a carbon on one side, there's a hydrogen on the other. And then for a ketone, it's a carbon and a carbon. And the only difference, hemi means that we have an OH on it. And then the acetal, like this means that we are halfway to an acetal. An acetal would have 2 OR groups on it. But a hemiacetal only has 1 OR group and 1 OH. So it's going to be a hemiacetal if it's from an aldehyde. So it has an H on here. If we had a carbon on the other side, then we would call this a hemiketal. It's just like a functional group like detail here. They react really, really similarly, and oftentimes they're just broadly called hemiacetals in like a generic blanket statement. But this class is a little bit more specific about it. For example, like for the summer, we don't even mention hemiketals. We just call it all hemiacetals. So we have our purpose to do these functional group transformations. Now, thinking about goals, well, we definitely need to add this OET on. So we need to make this OET, or I'm going to call it OR, bond added onto our molecule. But then in terms of bonds that we broke that pi bond. And so we can think about this reaction, and all of the steps in it are trying to accomplish these chemical goals. So for example, this step number 2, this is where we broke the pi CO. We accomplished that goal in this step. And then that also is the step where we made our OR bond onto the molecule. It created this at the same time that it broke a pi bond. And so step 1 was a setup to accomplish both of these goals, and then step 2 was just step 3, I should say, was just neutralizing our product. And so the last thing that we can do is right now, this is a specific reaction. I started with a specific molecule and another specific molecule for the alcohol. But I can generalize this as we are going to have a ketone or aldehyde with an alcohol and acid going to form a hemiacetal or hemiketal. And I'll write my alcohol here as ROH. Woof. So, I don't know what you're thinking, but maybe the thing I would guess you're thinking is like, this feels a little overkill. Like, this feels kind of like a lot for a reaction. But also, do you see how every single part of this, when we were approaching it, we were thinking critically about this reaction. We were trying to understand how it's working and trying to also see trends and patterns to help us see how other reactions and other molecules are going to work. This type of thinking and studying is going to be so much more rich than if you literally just verbatim try to like copy over and over the reactions. Like, the questions that we like to ask you on exams are ones where you're going to have to understand what happened and why in a really kind of granular way, but you're also going to have to think about these bigger picture things of like how we use reactions. And so this method of kind of studying at different levels of depth, one, I think is going to ultimately be more efficient for you. And then two, it's going to help you train you to think about these molecules for the different ways that you're going to be asked about it, from the full mechanism type question, new or known mechanism, to the box problems, to our kind of baby synthesis, where we're kind of thinking big picture. And, oh yes, I can zoom in on the generalization. So, any questions on this before we move on to kind of like normal section things? I know that this was kind of a lot, and it was also like, thank you for coming to my TED Talk. But does this at least feel like a method or a tool that you can try out with some of the reactions just as you are studying and see how it works for you? Like, again, if you come up with a better way, let me know. I would love to hear. But yeah. So one thing that I've done for y'all to help you with your studying is I have made a review sheet that is the last page of the section notes, where essentially I kind of do this process for you for these reactions in lecture 4, just to give you a template to see what kind of things to be paying attention to and maybe how to organize it for yourself. And so this is the toolbox here. And our compartments are going to be these little families of reactions that are very similar. And this is the next 3 big chunks that we are going to spend time in section talking about, of these different families that kind of react together. But for example, for the acid catalyzed formation of the hemiacetal, this is the exact steps that we just did in terms of summarizing the logic, generalizing it with the functional groups and everything. And this is like a great way. I love like a one-sheet summary of things, just to kind of cram and organize it and kind of figure out how to compartmentalize the information. The thing I will tell you is this is a trap. Having this and using it is not a substitute for your own studying. And like, there has been debate in past organic chemistry semesters of, should we provide you with this or not? And I'm like, at least for the first one, I think it's helpful to just have some scaffolding to see what this can look like. And again, the other thing I really like about this form of doing it is you don't have to deal with all the curved arrows here. You are putting it in kind of simple English, and this looks like something that's more manageable to study than all the arrows. Because even just when you are seeing arrows in your own study notes, you're having to interpret that. You're having to like think about it and what it's doing. And this allows you to just think in the labels. And so you're not having to do that extra translation stuff. But I hope that will be helpful as you're doing some practice and studying. And without further ado, let's pivot into real content instead of meta education. So, first thing that we're going to start off in talking about is redox. And this is kind of a reframing of what you've seen for Gen Chem. I know you all have spent some time with oxidation reactions, oxidation reduction, in Gen Chem. But oftentimes for organic chemistry, we don't care about all that. Like, that's very mathy. You're using equations. We mostly care about we mostly care about carbon, because we are in organic chemistry class. This is our main molecule. And as a shortcut for doing the whole like oxidation formulas and oxidation number, for carbon, we came up with this thing called oxidation levels. And the oxidation level is the number of bonds a carbon has to electronegative elements. So we have things at oxidation level 4, that's really only like CO2, and then this molecule, carbonic acid. Then in oxidation level 3, we have these carboxylic acid kind of functional groups. So carboxylic acid, an ester, an amide, a nitrile, which you all know from the exam. Then oxidation level 2, we have ketones and aldehydes. Oxidation level 1, we have alcohols, amines, and alkyl halides. Now, this might seem kind of arbitrary, but one thing that is really, really useful is to notice that things at certain oxidation levels or within the same oxidation level react in a similar way. For example, almost all the reactions that you learned for lecture 4 could be done on a ketone or an aldehyde because they're at the same oxidation level. They do very similar reactions. Lecture 5, you are going to be deep in oxidation level 3. You're going to be learning reactions of all the CADs. Then I think in like lectures 7 and 8, you're going to be doing things with these bad boys, oxidation level 1. So they're kind of grouping by how they react. Now, if we have a reaction that changes the oxidation level of a carbon, we call that a redox reaction. And we have made kind of our favorite reagents for doing oxidations and reductions in organic chemistry. And we are going to talk more explicitly in this column about the oxidizing agent, chromium trioxide. So if we are doing an oxidation, we are going to be moving up in oxidation level. So we are going to go from like 1 to 2, 2 to 3, or like all the way from 1 to 3. And chromium trioxide, she's fierce. She's out there on the dance floor. She has some symmetry about her like work, chromium trioxide. And more than that, she has a little sidekick that's like following her around. So her sidekick is either going to be pyridine, like a basic solvent to go with it, or it's going to be water. And we're going to talk about like when we use one versus the other. So looking at these oxidation reactions, these line reactions, so for these you don't need to know the mechanism at all. Let's look at each of these and see what oxidation level we are going from. Well, on the left we're at alcohols. So these are carbons that they're only attached to one electronegative thing, the oxygen. So these are all at oxidation level 1. And then for A and B, we're going to an aldehyde or a ketone. So we're going to oxidation level 2. So we're going up by 1 level. But then for this third one, we're going all the way to oxidation level 3, because this carbon has 1, 2, 3 bonds to non-carbon things, or to more electronegative things. So if we are just trying to go from oxidation level 1 to 2, that's when we use our pyridine sidekick. The way I think about the fake mechanism for this type of reaction is I think about chromium trioxide gobbles up hydrogens. So we look at the carbon that's connected to the OH, and chromium is going to gobble up one of the hydrogens and then create a double bond with the oxygen to make our carbonyl. Then, if we are trying to get all the way to a carboxylic acid, sure, we want it to gobble up 2 hydrogens, but the big thing is our product now has 2 oxygens in it, whereas the starting material only had 1. And so this H2O is actually going to be the source of our additional oxygen that we add into the molecule, incorporate into the product. And so that's why we need to have this different sidekick of H2O rather than pyridine. One thing to note is this can also take you just from an aldehyde, which is oxidation level 2, to a carboxylic acid. Like you could just do this and then add in our chromium with H2O and go to the carboxylic acid, or you can go all the way from an alcohol starting material up. Now, one thing that's kind of related to this that I don't feel like we spend a lot of time talking about, it has to do with how we classify functional groups. So backing up, carbons, not all carbons are created equal, and carbons we classify according to how many other carbons they are attached to. So for example, this carbon over here is only attached to one other carbon, so we call it a primary carbon, or sometimes we'll write it as 1 with a low degree sign. This carbon is attached to 3 other carbons, so it is a tertiary carbon. And this one attached to 4, it's a quaternary carbon. Okay. Well, we, for alcohols or alkyl halides, classify that alcohol or alkyl halide according to the type of carbon it's attached to. So we would say this is a primary alcohol because the carbon here that the OH is attached to is only attached to 1 other carbon. This would be a tertiary alcohol because the carbon the O is attached to 3 other carbons. So on and so forth. So the big thing is chromium. Remember, the way it works is it kind of gobbles up hydrogens. So if we start off with a primary or a secondary alcohol, we're going to be able to do an oxidation. But if we start off with a tertiary alcohol, and we tried to use chromium with pyridine or H2O, are there any hydrogens to gobble up on the carbon? No, that carbon has 4 bonds already. And so what we get is no reaction. So just something to watch out for these tertiary alcohols. And again, I think having the language here will help you be more specific for like which alcohols can be oxidized versus which ones can't. So that is our kind of first half of our redox of oxidation. Moving up in oxidation level, we use chromium trioxide. Now let's talk about the flip side of that, of doing reductions. So moving down in oxidation level. Well, when we are moving down in oxidation level, one thing that you might notice is we need to, at our carbon, start to add more hydrogens as we go down, generally speaking. So like, for example, going from a carboxylic acid to an aldehyde, you need to add a hydrogen to the carbon. And then from this to like an alcohol, this might need to be like an R here, and then this is CH2. But still, going from this to this, you're adding another hydrogen. So essentially, the issue is we need a source of hydrogens in order to do reductions for most of our carbon chemistry. So this family of reactions we call hydride equivalents. So we need to essentially add an H- to a molecule. And there are a couple of issues with just trying to add H on its own. So for example, let's say we just wanted to get a hydride and have this reduce a carbonyl by attacking it as a nucleophile. So NaH would be our hydride alone, our hydrogen with its 2 electrons, and it is a strong base, but it is a weak or poor nucleophile, I should say. So it is just not going to have enough energy to go and attack something as a nucleophile. It's great for a little acid base, like grabbing a hydrogen off of something and making H2 gas, but it's not going to do a nucleophilic attack on its own. Then you might ask, why not just like an H+, a lone hydrogen? Well, the thing is, we need our hydrogen to be a nucleophile to attack the carbon. It needs to have electrons with it, and an H+ is just going to be a single proton, no electrons. So what we need is something that is going to act like H-, but it is going to be more nucleophilic. And we call these things hydride equivalents. These are compounds that use elements in the group 3A, or like column 13 of the periodic table, specifically boron or aluminum. And in these compounds, you have this AlH4 or boron H4 structure, aluminum, lithium aluminum hydride or sodium borohydride are 2 examples. And I've just kind of generalized it with an X here. And the thing that's kind of weird is the electronegativities between hydrogen and boron, or hydrogen and aluminum, are exactly the opposite of what you'd expect. So like normally, like in an OH bond, for example, we know the oxygen's way more electronegative. It's partial minus, hydrogen's partial positive. Even in a CH, in CH it's pretty nonpolar, there's not a huge difference, but very, very slightly, there's a very small partial minus, partial plus on the hydrogen, because the hydrogen is pretty low in electronegativity. But my God, it's a race to the bottom with boron and aluminum. Even though hydrogen's electronegativity is 2.2, boron's are 2.04 and aluminum's 1.61. So in this bond between hydrogen and this group 3A element, hydrogen is more electronegative. It has a partial minus on it. And then the boron or aluminum is less electronegative, so it has partial plus. And so what it means is this sigma bond between the hydrogen and the group 3A element is really going to act like a hydrogen with a negative charge, which is exactly what we want here. So let's look at the reaction. Our line reaction here, we start off with a ketone or aldehyde, and then we add either our lithium aluminum hydride or our sodium borohydride. Either one of these would accomplish the same goal and get to the same product here of making an alcohol. So what we do with our reaction is our sigma bond, our sigma, oh, I put CX. Gosh, that is a typo. Sorry, this is our sigma hydrogen X bond. is going to go, and the sigma bond itself is going to go and attack the pi star CO and then push up. When we've done that, we have broken the pi bond and created this new hydrogen bond, a bond with hydrogen, I should say, on the carbon. And then to get to our final product, all we need to do is protonate our molecule. And so I just put this as like a general acid here because it depends on the different versions. And then we are at our alcohol. So it's a nice like two-step reaction, nothing too crazy. But a question that you might have is, why do we have two versions of this? Like, if they are accomplishing the same thing, why the redundancy? And my answer to that is, spoilers. Oh my gosh, it's going to come up later. We're going to talk about it later, don't worry. But for right now, they both accomplish the same goal. Either the sodium borehydride or lithium aluminum hydride. But also because this is pretty abstract, I do want to try to characterize them for you. So it'll kind of preface some of the different reactivities that you'll see with them in the future. So I call lithium aluminum hydride toxic masculinity, and then I call sodium borohydride soft boy. So toxic masculinity, lithium aluminum hydride is ready to pop off, is ready to fight people. It will react with ketones and aldehydes. It'll react with esters. It'll react with nitriles. It'll react with so many things that you haven't even heard about yet. She's ready to fight. Toxic masculinity. Now, because of that, because it is so reactive, we can't have like acidic hydrogens around. Because if we had even like an alcohol, like if we had, instead of doing this with an ether solvent, we did it with an alcohol solvent, tried to do it like this, lithium hydride's like, you want to fight, bro? And it's just going to grab the hydrogen off the alcohol and not react with the carbonyl that we want it to do. And so we have to be really, really careful. We have to use a solvent that's an ether. And ethers are like very classically not very reactive. And so we give the toxic, really like reactive thing a really mild solvent. And then we have to do a second acid workup step. So like our product at the end of step 1 for lithium aluminum hydride would be this. And then in step 2, we would add our H3O+, and this would go grab a hydrogen, and then it would be neutral. So that's kind of its character. Whereas sodium borohydride, soft boy, so gentle, so mild. So it is going to attack carbonyls, but it's not going to mess with like an alcohol. And so you can combine the source of hydrogen here, like an alcohol, in the same pot with NaBH4. You don't have to keep them as two separate steps. And so it's nice because this is a one-step transformation, whereas the other one's two-step transformation. It's also, because it's weak and mild, sodium borohydride really only reacts with ketones or aldehydes. It's not going to react with esters and all the other stuff that you'll learn about later. And so that's kind of the big difference that you're going to see, which again, you'll get more experience with as we go along. But I like to think of them as the hydride brothers. They're out here. Okay, so if we did a practice here with line reactions, let's look at this. So the first thing that I might do is be like, did a redox reaction happen? Did we change oxidation level? We start off here at oxidation level 2, then we're at oxidation level 1, and then woo boy, we're at oxidation level 3. Okay. So going from 2 to 1, did we do an oxidation or a reduction? Ding dong. We did a reduction. We went down in oxidation level. And then also, Evan, to answer your question, sodium borohydride, it can be with any alcohol. You could use ETOH, and the identity doesn't matter because the only thing that this matters for is it's a source of hydrogen. So we are doing a reduction. So we are looking at our hydride equivalents, right? Like this carbon right here has one hydrogen on it there, and then over here it has two hydrogens. So we need to give it a hydrogen. So we can either use toxic masculinity or soft boy. So I might use NaBH4 MEOH just to make it a one-step thing. Or, again, you could do the two-step version. 1, lithium aluminum hydride with ether, and then 2 H3O plus. And one thing, and it's going to be super annoying, if something is 2 steps versus 1 step, like this, you have to put 1 period and then the thing, and then 2 period and then the thing. Otherwise, you will lose points. Because if you just write them like this, it looks like you're mixing all of this in the same beaker. And so you have to be really specific about it being 2 step or 1 step. Then, now, going from alcohol, oxidation level 1 to oxidation level 3, we use our oxidizer, Miss chromium trioxide. And so now our big question is, do we use her with the sidekick of pyridine, or do we use her with the sidekick of H2O? And here, because we are going all the way up to oxidation level 3, we need another oxygen present. We know we have to supply H2O as our source of oxygen that gets incorporated in the product. And maybe actually one thing to point out, we could have done this whole thing in 1 step, going from the aldehyde to the carboxylic acid with CrO3 and H2O. So we didn't have to do the reduction. This is just like learning and growing and do you understand blah, 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 blah. Work. So, any question on this family, the hydride equivalent reactions, of what their purpose is, how they're doing their jobs?
I have a question.
Yeah.
So just like for the sake of lecture 4, like the practice problems and the problem set, so
Yeah.
if we need to use a hydride equivalent, it's going to be like one of those, right? Like we're not going to have to grasp for other ones?
Yeah, no. Exactly. Like, this is the thing. If you need to do a reduction for this class, your only options are these 2. Because, like,
Okay.
we are never going to expect you, right? Both not expect you and actively do not want you to find other reactions out there in the world. Like, they exist. There are other ways of reducing things. But we are wanting to see, can you take the tools that we give you and, like, learn to play the game of reactions with them? And so...
Okay, so we're just using what you give us here, like we're not going to need any extra to solve these problems. All right,
Ding dong.
thank you.
Yeah, totally. Cool. So now let's go on and talk about the carbanion equivalent reaction family. So the purpose, the whole goal that this family is trying to accomplish is they are trying to add an alkyl group to a carbonyl. And when we do that, when we add a carbon thing to a carbonyl, we make an alcohol. And that's the thing, like, making the alcohol here is not really our goal. It just kind of happens along the way. So, like, over here, to go from a ketone or aldehyde, and then to add in some new R group carbon onto the carbonyl, like, essentially this oxygen is just sticking around, and so it becomes an alcohol. But the big thing, that the whole purpose of this family is to create carbon-carbon bonds, which that's going to be like a huge theme of this class and Chem 27. Carbon-carbon bonds are both hard to make and hard to break. And so both us as like scientists in the lab and nature need to develop strategies for making and breaking carbon-carbon bonds. And this is your first one that you are learning, to make a carbon-carbon bond. So, I imagine it's like the little dog playing with the little dog toys of like the alkyl group and the carbonyl and going like, kiss. That's these reactions. So, your question first might just be like, if we need to add an alkyl group, why not just get a carbanion? Like, why not just like deprotonate like an alkyl group, have a negative charge on it, this thing goes and attacks a carbonyl. Basically, what do you remember about the pKa of like a methyl or methane or like an alkane? I remember off the top of their head. The pKa of that is going to be like 50. Yeah. So you would need like a crazy base to deprotonate that. Like, this is the whole thing of like, oh, did you hear about the explosion that happened the other day in lab? Like, they were probably talking about this if you're trying to deprotonate an alkane, like crazy. So again, this is the whole thing of like, okay, well, if this is hard to make or and like doesn't work for us, we need something that's going to look kind of like this. And so what we do is we use organometallics. So organometallics are compounds that have metals and carbon in them, essentially. And we want carbon to essentially have like a negative charge on it, right? Well, carbon has an electronegativity of 2.55. So if we want it to act like a negative charge, we need to use something that has a really low electronegativities, like less than 2. And those are typically going to be our metals. And so the metals that we most often use for this class are MgBr, like magnesium bromide, and lithium. Copper, that's in the summer, we teach a copper reaction around this time, but y'all have not learned her yet. And you might never learn her. Sad. Copper's cool. But here, the metal is going to have an electronegativity of less than 2. The carbon's going to be 2.55. So now this one's going to be partial negative. This one's partial positive. And so it's going to react like a carbanion. Okay, great. So this carbon-metal bond, this sigma bond, is going to do some attacking. Now, the mechanism for this is our carbon-metal bond is going to attack the carbonyl, push up. Then we are at our tetrahedral intermediate here. And then the second step that we do for all of these is we protonate it to neutralize. Wow, that looks very similar to the hydride reactions, where first step, the sigma bond between the hydrogen and the aluminum or boron attacked, and then we protonated it. Wow, we're seeing patterns. 4 reactions, all doing essentially the same kind of curved arrows. It's not that scary yet. So we have 2 flavors, again, for this one, just like we did for the hydride. And again, it will not be clear why we have 2 flavors until later. So for right now, these 2 methods are completely equivalent for you. Like, there's no reason to prefer one over the other. So the first version, if we use an alkyl group, R here is the alkyl group that we want to install onto the carbonyl. The first version is with MgBr. We call this the Grignard reaction. And everyone sees that and they're like, Grignard, don't do that. Be better. Grignard, yeah, with a yeah. And then this is the thing. This class, y'all just write ether. In my version of the class, we wrote specific ethers, like a specific molecule. And a really common ether is ET2O here, which is diethyl ether. And my way of remembering it was like, oh, well, this is a little oxygen bat. And Grignard kind of sounds like a vampire. And so, like, the vampires with the oxygen bat doing their, like, reaction, kind of flying around. Again, this is where you can see, like, we're getting a little silly. Like, I know that this is not, like, quantum mechanics, but hopefully it will make it more memorable. Or you can also think about just, like, who would have an ether? Probably some creepy vampire. I don't know. Here we are. So that's the Grignard reaction. And then if we use lithium as our metal, this is just called an organolithium. She doesn't have a fancy name. Both of these are split into 2 steps. So just like lithium aluminum hydride, these are really, really, really reactive. And so we need to keep any potential source of like alcohol or like a proton that's acidic in a separate step. And so oftentimes this second step where we have H3O+, is called an H+ workup or an acid workup. And like, we don't have to use H3O+ for this. Like, in our mechanism, literally, we just need some source of hydrogen. But you can imagine we could have also used hydrochloric acid. In some cases, if we have a strong enough base, we could have just used straight up water as our acid. Because, you know, water can act as an acid or a base. And so, like, in certain cases, we don't care what the acid is, and we'll just write an H+ workup. But here for the class, the way they introduced it, they specifically listed H3O+, so just when in doubt, go with that. But the idea is any acid would probably do. Just like, again, for ether, any ether would do. Diethyl ether is just my favorite. Cool. So, one thing that we need to know, in addition to just these reactions, reacting with the carbonyl, is it's going to be helpful for us to figure out how to make these actual reagents. How do we make the Grignard reagent or an alkyl lithium? And they are made from alkyl halides. So if we start with an alkyl halide and add magnesium, and with this superscript 0, that's just comparing it to like Mg2+, which we know is like an ion, and it's going to be like aqueous. Mg0 is the solid form of magnesium, like the metal from the earth. Literally what she does is she just kind of like slips in here, and then she becomes RMGBr. You don't need to know a mechanism for these formation ones. You just need to know the line reaction of like, okay, if I have an alkyl halide, how do I make it into a Grignard? I add Mg and ether. And then to turn into an alkyl lithium, you add 2 equivalents of lithium and ether. And that will make our reagent. One thing I put here is, remember saying that Grignards are really reactive and we have to keep our acid workup for a second step? Being a Georgian, a Southern peach, trying to do the Grignard reaction on a humid day is a pain in the butt. Because if you even have like a microliter of like water in a reaction flask, the Grignard will only react with the water and it will not react with the rest of your molecule. And so one thing that you're going to see as you start to do some practice problems is you can't use Grignards if there's an alcohol present. So like, let's say I had this carbonyl and I had this alcohol over here. With this, if I wanted to have like CH3 MgBr go and have a attack essentially up here, it would not do that. What it would do first is it would go and just deprotonate this alcohol instead. Just because it's so much faster to do an acid-base reaction than it is to attack a carbonyl. And so you'll see that in some practice. Don't worry about it for now, but just one thing to know about Grignards is they are strong bases, and the same is true for alkyl lithium. So let's try to do a practice here. So we are given this reaction and told to write the mechanism for the steps that we are responsible for a mechanism. Well, whenever we see a new reaction, what we should do is we should do a functional group analysis. What functional groups are present? So on the left-hand side, we know we have an alkyl halide, and we know that we have a ketone. On the right-hand side, we have an alcohol. Again, just kind of exam 1 skill you're going to be using every time you do problems going forward, essentially. So with this alkyl halide, and then our first step, Mg ether, well, we only know one reaction at this point that starts with an alkyl halide, and it's the formation of our Grignard reaction. So we are going to do step 1 here of adding our elemental magnesium and ether, and all that is going to do is insert itself between the carbon and the Br. And remember, we are not responsible for the mechanism of this. Mostly just because it kind of slips in, like there's not really a mechanism to be had. Okay, and then we need to go from this. So we have a Grignard and we have a ketone to an alcohol. And it appears we've made another carbon-carbon bond. So the thing that I am thinking about is I know for this reaction, this carbon at the base of the carbonyl becomes the carbon at the base of the alcohol, right? So let's use that as an anchor point to try to figure out the rest of this. Okay, so this carbon, green star, is this green star over here. Well then this methyl on the end is probably this methyl over here on the wedge. And then this OH came from the carbonyl, the O did at least. And then let's think about this numbering here. So if we call this star 1, then we could have 2, 3, 4, 5. If we call this 1, go around 2, 3, 4, 5. Ooh, we had a connection between carbon 5 and carbon 1 here. And that lines up exactly with what we would expect for our Grignard reaction. So what's going to happen is this sigma bond between the carbon and then the MgBr is going to go and attack the carbonyl and push up. Now, when that happens, we are going to make a 5-membered ring now, because this carbon 5 is now going to be connected to carbon 1. So, when I draw this, I have a 5-membered ring, and then I'm going to have my methyl and my O, but now it's going to be O minus, right? Because it initially had 2 lone pairs, and then I just kicked another set of electrons up to make a 3rd lone pair. And so now, to get from this to the product, what we have to do is our step 2 with H3O+. We have to protonate it. So it's just going to grab a hydrogen from there. And then we are done. Now, a question for you. This product has a wedge and a dash here, right? But is that a stereocenter? There are wedges and dashes. No, remember this is the trap. So if we look at this, these two sides are exactly the same. So it is not a stereocenter. And it's achiral. However, you could imagine this reaction could easily create a stereocenter if we just did something like add a methyl on one side. Then this whole like side chain over here on the left is different than the one from the right, then it would be a stereocenter. So these reactions can sometimes create stereocenters, which is something to watch out for. Cool. That's kind of intro to the organometallics carbanion equivalent family. So that's our second big family. Any questions on that before we go to the last family?
Yes, I have kind of a basic fundamental question that I think I'm still getting confused a little bit. Can you zoom back in to that practice, please?
Yeah.
Okay. So the carbon chain, specifically the ketone.
Mm-hmm.
When I look at that, I thought there were 6 carbons. Can you correct me where I'm wrong?
You're so right. You're so right. There are 6, and the 6th one is right here. The reason why I did my numbering this way is because I cared about the carbons in the ring. Because when I was initially starting to map the starting materials onto the product, I was like, okay, I can account for this carbon, I can account for this oxygen, and also on one side there's a CH3, a methyl. I can account for that already. So then I was just like, let me only number the ones in the ring to get that 5 members of the ring. Yeah.
Okay, perfect. Thank you so much.
Totally. Yeah. Okay. So let's talk about the last family. And the last family is a little bit all over the place. But this family is the reversible carbonyl additions. So the purpose of these, more so than the other ones, is to reversibly interconvert between a carbonyl, a ketone or aldehyde, and some other functional group. And many of these functional groups are new to you, like ones that you have not heard names for. They were not like lecture or exam 1 functional groups. So again, for the reversibility, both the carbanion equivalent family and the hydride equivalent family, those reactions are irreversible. So they are only going forward, that you can't go backwards at all. But the weird thing about these is all of them that you can go backwards. Now, all of these reactions essentially fall into one of 2 camps. They can either be acid catalyzed or base catalyzed, mostly just because reactions without a catalyst for these reversible ones are super slow. So let's introduce the other functional groups that we might want to turn this into. Well, one kind, and they spend a lot of time in lecture on this, is the hydrate. So a hydrate is a carbon that has 2 OHs on it. It's also called a geminal diol, which I just like that because it's like, ooh, Gemini, twinsies. But hydrate, sure, that's more like biochemistry. But the pure organic chemists, they get to also be astrologers here, Gemini. So the hydrate, essentially we need an OH to add. And that's going to come in the form of, we have water and we have either acid or we have base to help us out for that. So that is going to form our hydrate. That's where we get the other OH from. Then the hemiacetal/hemiketal, oh my gosh, we already talked about her. So we've already seen one of these in a lot more depth. So we're not going to spend as much time on it. But we can do this either with an alcohol and acid or with an alcohol and base. And then the last one is only in base. It's the cyanohydrin formation. So CN minus, her name is Cyanide. Like, she used the cyanide that you're thinking about, used to like poison people. And hydrin, hydro, water. Cyanohydrin, OH and CN together. And again, right now, these all kind of feel like, well, what's the purpose of this? Well, in the future, you will learn reactions that start with a hydrate and go on and do other things. Or you'll learn reactions that start with a cyanohydrin and go on and do other things. Or start with a hemiacetal, blah, blah, blah. Again, we are trying to like build different moves for our little chess pieces, molecules, of like how can they move across the chessboard. And these are all different things that we can transform them into. Now, they all have their own mechanisms, but like we've seen, a lot of these mechanisms are really similar across all of Lecture 4. So, the general scheme for acid mechanisms is a 3-step mechanism where first step, you protonate the carbonyl. That lowers the energy of our LUMO, makes it a better electrophile. 2, some nucleophile goes and attacks the protonated carbonyl. And then 3, we like neutralize the molecular deprotonate. So that's kind of our 3-step process for doing the acid mechanisms. Then in base, the nice thing is, instead of needing to have, remember we talked about our HOMO-LUMO gap, right? Our LUMO is our electrophile, our HOMO is whatever is doing the attacking. And in acid, we lower the energy of the LUMO here. We protonate that carbonyl, we make the gap smaller. But in base, what we do is deprotonate the nucleophile to make it higher energy. Like we have an OR minus instead of just a neutral alcohol, and that's going to raise the energy of the HOMO. And so because we have negatively charged things, typically negative charged things with an O or a negative charged thing with a CN, these can just attack the carbonyl directly because they are better nucleophiles. They are higher energy donors. And so our steps for this are step 1, the nucleophile just attacks the carbonyl because it's already a good nucleophile. And then second step, we neutralize or protonate to make it done. So that's kind of the general schema. Let's put this, or the other thing is like with reversibility here. Did Serenia talk about, this is gonna sound like heady, the principle of microscopic reversibility? Like, did that come up? Maybe not in so many words, but do you remember we're doing like energy diagrams, right? The principle of microscopic reversibility basically says when you zoom in and look at molecules, if it can do the forward path, it will also do the reverse path in the exact same way. And so what it means is for these reversible reactions, you are able to undo the reaction by literally undoing the steps. So for example, if your last step in this base mechanism was to protonate it, then to do the reverse reaction, your first step is going to be to deprotonate it. Then, if your step before that was a nucleophile attacking a carbonyl, now you need to reform a carbonyl and kick off something. And so you are literally undoing the arrows in exactly the same way as the forward direction. So, I missed a question from earlier. I'm going to get it really quick. So over here, like the MGBR, when this goes and attacks, literally the carbon in this reaction is like, I'm taking the children and leaving, and steals away the electrons. And the MGBR just kind of sloughs off. Like, she's just now in solution, MGBR, like, ready to hit the scene to find some other ionic partner. But yeah, she just, like, falls away. It's kind of, I don't know. It's a little harsh, but yeah, she just falls off. But with that in mind, we've talked about the microscopic reversibility and everything. Let's look at these two mechanisms, and that'll be kind of our last 10 minutes here. So, again, what we do when we look at a reaction, the first thing is we should stop and identify our functional groups. So, we have an alcohol, we have an alkene, and over here I see we have an alkene. So, if I'm seeing the alkene both in the starting material and the product, I know we really didn't touch this. So I'm going to say, hey, that's helpful for us when we're trying to map the starting materials on the product. But, like, she did not do anything in this reaction. Then, what is this functional group? It's kind of tricky. So we have, on a carbon, an OH and an OR. And what do we call that for, like, exam 1? Okay, people are close. So ester, remember, you have to have a carbonyl and then an OR. So not ester. And then for an acetal, you need to have 2 ORs. What's the version where you have an OH and an OR? It's halfway to an acetal. So it is a hemiacetal. Risa got it. Thank you. Thank you. So we have a hemiacetal. Okay. And then this one over here is one of our new ones. We have a nitrile and an alcohol attached to the same carbon. So this is our cyanohydrin. Bloop. So right now this looks crazy. We don't know any reactions that take a cyanohydrin and an alcohol and make a hemiacetal, right? So this is where we can use your ignorance to your advantage. If you see a cyanohydrin, you currently only know one reaction with a cyanohydrin, and that is going from a cyanohydrin back to a ketone or aldehyde. Like, that's the only thing you can do. Okay, so let's do that. Well, in the Ford reaction, if we were trying to make this, our last step was protonate. So what should our first step be of the reverse reaction if we're trying to go from cyanohydrin back here? Well, it should be deprotonate. And, oh my gosh, love, we have a base, so we can deprotonate. So I'm going to draw this OH bond explicitly. I have my OH minus, and she is going to go and deprotonate, step 1. And I might need more space, so I'm going to write small. Okay. Well, then we need to undo the first step. The first step was something attacking the carbonyl, like a CN minus attacking the carbonyl. We need to undo that. So we need to reform a carbonyl, and we need to kick off a CN minus. And this is our lone pair push. Iconic, legendary. My little story with lone pair push is there is a hydrogen here, but this is a tetrahedral intermediate. I imagine the lone pair push as like a really cinematic moment in like kind of an episode of Friends, maybe. The carbon is an apartment. 4 people live there, but one of them has been getting fed up. Negative charge. Says, Nitro, we don't like you here. None of us like you. I am going to kick you out. I'm going to push you out. Push down the electrons, make a double bond here, kick off the CN. And then our product that we get out of it, we've just kicked off CN minus. And now we have a CO double bond. And I'm just going to draw that hydrogen over here now. The hydrogen that was over here. It still stayed attached to the carbon. It's still in the apartment. Work. Oh, and then I'll make my arrows red. So this whole thing that we've done so far is the cyanohydrin hydrolysis reaction. We've gone backwards. We've gone back to a carbonyl from it. We've gone from this to this. Okay. Then, now, we need to make a hemiacetal. And if we look at our functional groups now, we have an alcohol, and we have an aldehyde, and we are in base. Can we make a hemiacetal from an alcohol and an aldehyde in base? Bada bing, bada bang. Again, for hemiacetal, you only know one reaction that can do it, and it is either in acid or base, like flavors of the same reaction. So, okay. So, essentially, we need... Ooh, okay. So this oxygen needs to be the thing that goes and attacks. This is our alcohol, right? But right now, this alcohol is neutral. And remember, like, the neutral alcohol isn't good at doing a nucleophilic attack for, like, a normal carbonyl. And we're not in acid, so we can't protonate this and make this a better electrophile. So what we are going to do is we are going to use our base. And we are going to deprotonate this to make it a better nucleophile. And the other thing that I'm going to do, and this might be a little psychotic, I'm going to do a slightly different color to indicate that we're doing a different reaction here. So, we still have our aldehyde boy over here. O minus. And the OH, when it grabbed the H, what it made was water. And over here in the first step, it was a similar thing of water came off. Okay. Well, now we have a really good donor with this high energy O minus. So it is going to go and attack the carbonyl. Oop. Like this. And now we hope that that's going to make a little ring that looks like this. Let's see if it does. So I'm going to say that that's probably going to mean that this oxygen down here is this oxygen over here. And then I'm going to number 1, 2, 3, 4, 5. So then 1, 2, 3, 4, 5. It's going to work out. So the sixth member of the ring is that oxygen itself that I called star here. And then I see between 2 and 3, there should be a double bond. Then there's a methyl on 2. Between 2 and 3, there's a double bond. There's a methyl on 2. Thank goodness. Thank goodness. Okay. So I'm just going to go ahead and draw the 6-membered ring looking like our product. And then the big thing is over here where we attacked, this is going to make an O minus, where our OH is going to eventually be. Now, question for you. This one right here, is that a stereocenter? Is it attached to 4 different things? Yeah, the hydrogen, the O minus, the O with all this other junk, and then the carbon stuff. So it's a stereocenter. And this stereocenter could be R or could be S. Like, essentially, this could have attacked from the top face of this pi star. Like, it could have attacked up here, or it could have attacked on the bottom, and that's going to change which one. So to indicate that we're going to get either one of these, what we do is we just draw one version of it. So I'm going to draw the wedge version, and then we put a plus minus to indicate that also the dash version is possible. So then our last step, going from here to the end, what do? Well, we need to add a hydrogen onto the molecule. So we are just going to take our water that was generated over here, and we are going to steal back a hydrogen from it, getting to our product. So this reaction here was the hemiacetal formation. So with this, and we're not going to do this last example together, I'll record it for the video for later, and you can watch it back to see it for extra practice. But with this example, you can really see this feels a lot more difficult than like the earlier one that we were doing. Like here with this, like Grignard, this was just kind of really regurgitating the arrows that were literally drawn right above for you. The hard part comes when we start to stack reactions together. And we start to do these kind of, like, we just wrote NaOH over here on a catalyst, but we did 2 separate reactions from this lecture. And the hardest part of it was figuring out what those reactions were. Because once we figured out what the reaction was of cyanohydrin, we're doing the hydrolysis, then we know the arrows from our lecture notes and from our studying. And then the same thing here for the hemiacetal formation. If you are not doing this tagging of functional groups, and like connecting the tags of the functional groups to the reactions in lecture, it's going to be real rough, and like it likely is not going to be correct, because otherwise you're just kind of like trying to like make it work models, and like that does not often agree with the answer key or what the molecules are actually doing. And so thinking about this as the framework of like, how does this example that looks hard and difficult and like something I haven't seen relate to the reactions I have seen, that's going to be your real challenge. So with that, I will stop here for today. Thank you for coming to section. I hope this was helpful with some of the study strategies and starting to do these kind of first reactions. And then I will be sticking around here for my help room hours. So feel free to stick around and ask questions. Have a good night.